Good afternoon, everyone, and welcome to Quantum Computing. Today we'll have our first lecture. I'm Patrick Launer, and Horst Kuhnhardt is with me here as well. We're both teaching the course. I'm teaching the majority of the lectures, but Horst will also teach some of the parts. Today we will start directly with a motivation of why quantum computing is so interesting and what all of this course is about. And once we've done that motivation, we will switch to the introduction for this course with a few notes on the organization of the course and the examination and so forth. And then I'll continue with the introduction, and then Horst will do part of the introduction, and probably we will still have some time to revise some of the maths we need for this course. But we'll start directly with a motivation why quantum computing is so interesting in this introduction. And the key question is, how do you speed up an algorithm? So when you study courses like algorithms and data structures, it's all about finding efficient algorithms. And that's actually what we do in most of computer science. If we can compute something, we want to compute it efficiently. And in an algorithms and data structures course, you learn lots of things, or in a programming course. For example, you could do profiling or optimizing statements in order to speed up an algorithm. As one suggestion, you just try to find the inefficient parts and you try to eliminate them or amend them, and then your code will run quicker. And I want to know from you if you have any other suggestions what we can do in order to speed up an algorithm. Maybe don't look into the slides. If you have any suggestions how to speed up, maybe you can just raise your hand here in Zoom and then go ahead or send a comment in the chat. Whatever suggestions you've got, how we can speed up an algorithm, I'll be most happy to see what you think, and we'll collect some of your suggestions. One student said we could do vectorization. Yes, that's one thing. So we apply the same operation to multiple entries at the same time. For example, we use vectorization a lot to deal with vector data and matrix data and try to eliminate loops and rather apply the same operation all over. And for that, we need some degree of parallelization. So we got this as a comment, which is also correct. If you have any other comments, please go ahead or raise your hand here in Zoom. I'm proposing we could just choose a different implementation of that algorithm, maybe one that runs quicker. And I'll see if there are more suggestions from you. Otherwise, I'll just go ahead. And I will also turn off my camera, otherwise the recording will just get unnecessarily large because you've all seen me now in case you haven't met me before. And I don't know, Horst, if you keep on your camera or turn it off, but for me it's personally easier to turn it off then. And these were your suggestions. There are more suggestions. We could, for example, do parallelization. This was mentioned. Or we try to improve the complexity of an algorithm. For example, when you look at sorting algorithms, there are inefficient ones like bubble sort, which have a complexity of O of n squared. And there are more efficient ones like quicksort or merge sort, which are O of n log n. Well, quicksort is O of n squared in this unlikely worst case. Let's just pick, for example, merge sort, which is O of n log n. Are you all familiar with the O notation? If you're familiar with the O notation, maybe just thumbs up. If you're not familiar with the O notation, thumbs down or red, because this is a very interdisciplinary course. So it's not just students from computer science. The course is open to students in other subjects, but I only see positive responses now. If you're not familiar with the O notation or you want to revise it, just check my lecture recordings of the algorithms and data structures course that I taught last semester. And in that course, we discuss the O notation in detail. Just in a few sentences, what this O means. O means that the number of so-called primitive operations in your code or in your algorithm, like an addition, a function call, a return, a multiplication, whatever, these are all so-called primitive operations. And when you work on an input that is of size n, then the order of operation of primitive operations you would need would somehow depend on n. And for example, n squared is far worse than n log n because n squared grows much faster. There are other notations in addition to O, like omega and theta. And it's not the number of operations that this refers to, but the order of operations. So constant factors and lower order terms are eliminated. But obviously, n squared grows much quicker than n log n, and we prefer algorithms with a better complexity. Again, if you need a revision, take a look at my Algorithms and Data Structures course, and you find the recordings on YouTube as well. And this course, as all of my courses, is being recorded on YouTube. If you send something in the chat, you will not be identified. If you turn on your mic to ask questions, you would appear in the recording. And the recording will also be available on YouTube. So if you want to keep your total privacy, just send your questions via the chat. And we want to make this course available to as many students as possible. So we'll also share it via YouTube. And one other approach to speeding up an algorithm is quantum computing. Because quantum computing, as of today, looks promising, so we can solve certain computational problems much faster than classical computers can do. It's important, not all problems, but certain computational problems, because quantum computers, they take advantage of quantum mechanics, and thus they allow us to do quantum parallelism. So quantum computers are inherently parallel, and that kind of parallelism can lead to improved complexity classes for certain problems. Not for all problems, but for some. And the goal of this course is to look at quantum computing, what it is. We'll look at the underlying maths for quantum mechanics. Then we'll look at fundamental quantum computing operations. We'll see quantum algorithms, and we will see how this runs on real quantum computers. And we'll look at all sorts of applications like machine learning, encryption, and so forth. And in order for this, what I've just said, to make it more tangible, we will discuss a little bit more now about quantum mechanics and one example algorithm, and then we'll look at the administration and organization of this course. Who of you has had some exposure to quantum mechanics before? And if you've dealt with quantum mechanics, maybe thumbs up or thumbs down. And if you have come across it, maybe just share something via the chat where you have studied quantum mechanics, and if you've seen any applications of quantum mechanics. There was just one thumb up. I came across quantum mechanics in high school in the final year, and because I took physics as one of my key courses in high school, and we discussed some quantum mechanics. But in that time, that was in 2007, 2008, when I finished high school, so the last year, and I had no idea that all of this could be applied to computing. But there has been lots of progress in the last 16 or 17 years. So one person had raised his or her thumb. I haven't seen anything in the chat yet, but feel free to still post how you have dealt with quantum mechanics. And quantum mechanics, it looks like it's something purely from physics, but in fact, quantum mechanics can be seen as a generalization of the laws of probability. With probabilities, you deal with regular probabilities, you deal with the one norm, but with quantum mechanics, we deal in the two norm. If these words don't make sense to you yet, you'll see this in the coming weeks when we look in detail into quantum mechanics. And we are not dealing just with real numbers, but we will in fact deal with complex numbers in the two norm. And this in fact allows us to build a generalization of the laws of probability theory. And that generalization will be used in quantum computing. Obviously, we need a link to physics as well, but quantum mechanics can be seen quite independently of physics, in fact, as a generalization of the laws of probability. And you may notice, so if you have taken my courses before, you have seen this, that sometimes there's a lot of text in the slides. I'm not reading out all of this. Sometimes it's just for you as a revision or further reading. So sometimes there's quite some text in it, so you don't need a lot of extra materials. So quantum mechanics goes back to physics, but it can be seen quite independently. And then it's interesting for computations, for example, theoretical computer scientists, and so forth. But we'll still make some link to this physics in this course, not too much, but we'll see quantum mechanics largely from a perspective of computation and a generalization of the laws of probability. And now I'll have a problem for you. Imagine we have a set V that has n many values. For now, it can be integers, what we store in V, but it can be totally different types of data. And we have n many values in our ZV. S0, S1, up to Sn minus 1. It can be integers, but could be some other objects for now. But you could start with integers. And I have a function C that is a condition function, and I pass an element Si, so any of these elements here can be passed, and there is a specific element I'm looking for that is called Sx. And the function C will return 1 if the element Si that I have passed is equal to Sx. If it's not equal to Sx, so Sx is some specific value I'm looking for. And if Si is not that specific value, then I return 0. And now we have a task. We want to find the value Sx in V. And that means one of all of these n values is exactly the value I'm looking for in my set V. All the other values are not Sx, only exactly one of them is that one. And I want to find that one, so that value in V for which the condition function returns 1. We can try to implement this in a simplified way in Python. We could say that V is the set of integers from 0 to 9, and there is some secret value Sx, which is that one I'm looking for. And we could, just in a simplified way, implement this. So we can say V is the values 0 to 9. So, and another question, are you all familiar with Python in this course? If you know Python, thumbs up. If you have not done Python yet, maybe thumbs down, because it is an interdisciplinary course. I only see where I see one thumbs down, and it's important. This is not a programming course. We'll mainly do maths and algorithms in this course, so you don't need to be a Python expert for this course. If you know Python, however, it will be very helpful, especially because there will be some lab problems. But I'll talk more about the examination later, but don't get scared if you haven't done Python. We'll just use Python in a few examples because Python looks like pseudocode, which we can actually execute. And now I create V with the range function. Range of n means values 0 up to n, where n is excluded. So the value is 0 to 9. Technically, we're creating an iterator, but that doesn't matter for now, or a list eventually. A list is not a set, but as I said, it's simplified. I don't care if this is now a list or a set. And I have my function C, the condition, for which I pass some value. And as before, when I define C, I'm checking if the value I'm passing is my secret value. But the secret here is blanked out. So we don't know what the secret is. It's just some value we're looking for. And if that's the case, we return true. Otherwise, we return false. So I have just implemented the function from before. And my task was to go through my whole set V. In this case, it's a list, but it doesn't matter. To go through all the values. That's why I have the function here, solve it. And I go through all the values in V. So I start with the first value in V, and I check if C of X, that means if C of X returns positive, I return X. If this loop runs through and doesn't return anything, so the loop finishes, I return false. Then I have not solved this problem. What I'm doing here is, in fact, I want to find out what is the secret, the value I'm looking for. And for that, I go through V, and if for some input X, Cx is positive, I return it, and I'm done. Otherwise, I return false. This is the problem I'm solving. And since most of you are familiar with complexity of algorithms, I want to know from you, what is the complexity of this algorithm? What I have here is a black box search. A black box search means I don't know how the search works or how this condition works inside, because this is some secret. I cannot look into it. So you're all familiar with complexity theory. And please, without looking at the slides, what's the complexity of the black box search algorithm that we have just implemented? O of what? And we got this as an answer. It's O of n, because the O notation always refers to the worst case. And in the worst case, I have to look at every entry. Obviously, I could be lucky that the first entry is my secret or the second one. But in the worst case, I have to look into every of them until I'm done, because it could also happen that none of them is actually the solution. So O of n. Now, in a classic introduction to algorithms and data structures, you learn how to speed up, for example, an integer search. And what you learn is the binary search. And the binary search would solve you this problem in O of log n if the values in your data set can be sorted. If you can sort them with binary search, it needs O of log n to solve the search problem, but it's not a black box search problem anymore, because you can bring order in it. And now imagine you cannot bring order in these objects, because it's not necessarily integers. It could be something totally different objects that you cannot sort. And there is a black box search. Then binary search doesn't work anymore. And in traditional computing, you need O of n much time. Concretely, we can even say it's not just O of n, but omega of n, because I definitely need n time as the minimum. But with a quantum computer, and this is where quantum computing becomes interesting, we can solve this in O of square root n much time. We can do the black box search with a quadratic speedup compared to classic computing, because it's not O of n, it's square root of n. And now, if this looks like totally surprising to you, something you could never imagine that this would be possible in traditional computing, maybe send some reaction or whatever in Zoom, if this just looks amazing and something that you would just never imagine could have happened. So when I saw this for the first time, I was in fact very surprised that this was possible. And it's not possible with classical computing, but possible with quantum computing, because we take advantage of quantum mechanics and quantum parallelism, and we use an algorithm that is called Grover's algorithm that provides us with this quadratic speedup. Now, we will not discuss Grover's right now. Grover's algorithm will be mentioned later during the term. But today, we will look now a little bit at what a quantum computer actually looks like. Because what I've said is we have quantum algorithms, but somehow we also need to run them. on a quantum computer. And meanwhile, there have been quite a few vendors around quantum computers. So quantum computing goes back to the 80s when Feynman proposed the concept of quantum computers, that one would use quantum mechanics for massively parallel computing, but no one knew how to build these machines. And in the last 15 years or so, more and more vendors have started to pop up that sell quantum computers. One of these vendors is D-Wave. If you Google D-Wave, it's one vendor that gets some criticism because some of its challengers or some people claim what D-Wave does is not proper quantum computing. In fact, it's a so-called adiabatic quantum computer, not a universal one. But what these architectures mean is something that we will teach in a couple of weeks. But it's just one vendor for now. And D-Wave offers multiple types of quantum computers. For example, a few years ago, they released the D-Wave 2000Q. And in your traditional computers, you have bits, and a bit is either 0 or 1. And in quantum computing, we deal with qubits. And a qubit can be 0 and 1 in parallel. And that gives us parallelism because it's with a certain proportion in 0 and with a certain proportion in 1. And then if you combine lots of qubits, you can in fact get a speedup. And the D-Wave 2000Q has 2048 qubits. If you look at other vendors, for example, from IBM, they have less qubits, but we will look into these architectures in a few weeks. It's very important. You cannot just compare D-Wave with IBM. It's totally different approaches. So you cannot just compare the number of qubits. And in fact, the D-Wave 2000Q, it's a huge box here, but most of it is just for cooling. The actual chip is just a small piece inside. Because that chip is made of niobium, it's a metal, and if you cool it down to 0.015 Kelvin, so 15 millikelvin, which is close to absolute zero, so minus 273 dot something Celsius, then niobium becomes superconductive. If you want to buy a D-Wave 2000Q, you need to spend $15 million upfront, plus probably at least $1 million more per year for the cooling. You can, however, also access some of the machines that D-Wave runs themselves at their office or at their data center. And you can get an account with D-Wave and you get 1 free minute per month where you can run your computations. You can also buy more time if you wish. And what you're doing is you have something that looks like a Jupyter notebook, and you can run this and access the D-Wave 2000Q or some of their other machines. And these computations, typically when you run them, it takes a few milliseconds. Like I've run some experiment here, took 0.3 seconds. So I have 59 dot something seconds left. And if I need more time, I need to wait for next month or upgrade my account. And it's important, this is not a marketing lecture for D-Wave. It's just one vendor out of many. And we'll look at more architectures in a couple of weeks. Now, if you have taken one of my lectures before or not, I'm just curious because we have lots of exchange students. Maybe send me a thumbs up if you have ever taken one of my lectures before, or thumbs down if you have not. Because this is an elective open to everyone in Deggendorf. So there are also students from other departments or exchange students, whatever, that I have never met. So almost half, a few more reactions that have met me before. So in each of my lectures, what I always show in the beginning is the map of computer science. This is something that started to appear some years ago on the internet for computer science, for maths, which actually provides a huge overview of the field. And then you see things like computational complexity, computer architecture, supercomputing, computer vision. This map, I think, provides quite a good picture of computer science. And then I always highlight which areas are actually interesting to this course. So in this course, it's all about computational complexity because we want to improve computational complexity. For this, we take advantage of quantum computing. So there's quantum computing here. We do parallel programming. We need to think about computer architectures. We are in the field of supercomputing. We will also look into algorithms, obviously. We will have some links to machine learning, and we will have some links to cryptography and information theory. And then what I always do next is I try to zoom in into the highlighted areas and cut out or crop the rest from the map. So you can now get a little bit of an understanding what we're doing, and computational physics is also of relevance to this course. So it's just to provide you a look into the big picture, what we're actually doing in computer science. Now, what are the objectives of this course? It's an introduction to quantum computing. There will be lots of theory, but we'll have a good balance also with applications. But the first few weeks will be lots of mathematics because we simply need to build a foundation for all the applications that will follow. I want you to be able to apply theory to real problems. Today, there's a certain state of the art of quantum computing, and we expect that this will massively improve in the coming years and decades. So I want to prepare you for this quantum future in this course, and so that you're also able to understand new problems that are coming up in the next few years or decades, and that you know when quantum computing is helpful and how to apply it to these problems. And we will also look at some current research problems and think about how quantum computing might evolve in the next few years. What you need to know to succeed in this class is mathematics. In particular, we need linear algebra, and we'll combine linear algebra with complex numbers. If you have an understanding of algorithms and data structures and programming, this will prove to be very helpful, but this is not a programming course. So the more knowledge you have in these fields, the more helpful it is. But if you're from a different department, say engineering or business information systems or whatever, that's okay too. You largely need maths to understand the foundations of this course, and based on linear algebra and complex numbers, we'll build all the foundations we will need. And if you have any questions, let me know. Later today, we will start also with a revision of complex numbers and linear algebra so that we are all just on the same page. The workload of this course is the following. We meet weekly for 3 hours for lectures. Later during the term, there will also be some lab sessions, but for now, it's lectures. And we will not do lectures the whole term. We will do lectures for about half of the term. And then you will be preparing a seminar presentation, which is the examination. But I'll say more about that in a moment. Now, this course is 5 credit points, ECTS. That's the unit we describe the workload with of a course in Europe. And 5 ECTS means something. 1 ECTS is equivalent to an expected workload of 30 hours during the whole term. And 5 ECTS means the expected workload is equal to about 150 hours. Now, a term takes 15 weeks. That means you have to spend about 10 hours per week on this course if you want to take advantage of it. It's the same with other courses that are 5 ECTS. And now going to this lecture is only part of your workload because you need to spend more time on, for example, revisions, doing some exercises, doing some further readings, work on lab problems, maybe preparing for this class, and eventually also prepare your seminar presentations. There are students who spend less time on this course, others spend more. Also depends on what you expect to get out of this course. But if you just follow the lectures, it's probably not enough because it's lots of maths and it's a heavy course. Most of what I do here is provided in the slide deck. There is a second slide deck by Horst Kuhnhardt, and I provide some more information on the whiteboard, concretely on my iPad, especially lengthy maths and calculations. You will find them in the slides in which they are super well typeset, but I derive all of this then on my own on the whiteboard, and we'll discuss it slowly, and I include lots of exercises in between. So as I said, the lecture part takes about half of the term, maybe 6 sessions or 7 sessions. We'll see how quickly we move on. And your examination will be in January. And if you look into the iLearn course, we have already communicated the date of presentations. And concretely, all the seminar presentations will take place on January 11 and 12, which is a weekend. And you need to choose a seminar presentation on your own that is related to quantum computing. You don't need to choose this now. Later during the term is the right time. Once we have made progress with this course, Horst Kuhnhardt and I will also provide lots of suggestions which topics you could pick. It can be topics related to technical or business problems. Most students in this course often come from AI, so they pick something related to machine learning. Sometimes there are engineering students, they pick maybe something related to quantum computers for engineering problems or how to manufacture quantum computers. Some students think about business potentials, and you will do your seminar presentation in groups of 3 to 4 students on that weekend in January. So the schedule is, there will be lectures until sometime in November, December, depending on how quickly we proceed and how quick we are every week. And at some point until early December, you need to pick your seminar topic. But it doesn't matter now yet, because we first need to get the foundations before we think about seminar topics. But there are books in which you can find seminar topics in ResearchGate and Google Scholar. So there are lots of ideas and lots of resources, in fact, when it comes to quantum computing. And sometime in early December, late November, early December, you will finalize your seminar topic and you will discuss your seminar topic briefly with me that I approve it. And then you will work on your seminar presentation. I'm available if you have any questions, and in January we will do the seminar presentations. And the lectures are via Zoom, because the lectures are on Friday afternoons, and it's available to all the students at our university, including the campuses in Cham and Pfarrkirchen. So the only way to reach all of you is via Zoom. And your seminar presentation on the weekend, January 11th and 12th, will take place on campus. And there will not be any alternative dates or online options. All the seminar presentations will take place on campus on that weekend. There are also some slides about how your seminar presentation gets marked and all of this. Your seminar presentation as a group will take 15 minutes, and there will be some time for Q&A. But I'm not talking about the details of marking now, because this is only something that matters when we discuss actually which topics you will be presenting, and the marking will come last. And I said there's lots of text also in some slides for you to have a good revision. There are also some good books about quantum computing. And the book we'll be using largely in this course is called Quantum Computing for Computer Scientists. And the reference is also in here, if you're looking for the book. The book appeared in 2008, so it's 16 years old, but that's no problem, because the book largely covers maths. And in that regard, the book is totally fine. In 2008, there weren't really quantum computers available on the market yet, or extremely limited ones. So the book is not up to date with that regard, but for that we use other resources. But the book is super helpful for the maths and algorithms. If you're specifically interested in how to apply quantum computers to machine learning problems, there's another book by Maria Schult and Francesco Petruccione. It's called Machine Learning with Quantum Computers. The second edition appeared 3 years ago. And if you're interested in maybe the big picture about quantum or quantum computing and its links to quantum mechanics, computational complexity, computability, foundations of theoretical computer science. There's a super good book by Scott Aaronson, and it's called Quantum Computing Since Democritus. That book is not easy to read. It appeared 11 years ago, but it really, if you're really interested in the big picture of quantum computing and its links to computational problems, theoretical computer science, and some advanced physics topics, then this is the ultimate book on the market. But you're obviously not expected to know all of this for your seminar presentation. The key book is this one here, Quantum Computing for Computer Scientists, for the foundations. And then for your presentation, you pick the resources you wish to have. But if you're just super curious and you have lots of free time, read this book and you'll get the big picture. I read it last year during the summer, I think. Was not an easy read, but gave me lots of new insights as well. You have noticed probably that we have the lecture recordings available of last year on YouTube. This one here today will also appear on YouTube, and I'll update the link in our iLearn course. There are just minor improvements compared to last year, because last year the course got a big update, and this year the update is smaller. There's also one thing I need to talk about. It's that this course is limited to a certain number of students, and I received lots of emails in the last few days. So the thing is, Horst and I started offering this course a few years ago for the first time. In the first round, the course had 45 students, and we were very happy because it was the first time we offered this elective, and it's a tough one. Then in the following year, we had 90 students taking the course, and last year it was about 180 students. And Horst and I struggled to examine all of these seminar presentations in a feasible amount of time. And we are unable to offer even larger seminar groups that have even less time than before to present. So we had to say 180 students last year was very cool, and we're very, very happy about all the students wishing to take this course, but it's purely an elective. It's not a mandatory course for anyone. So we somehow had to limit it this year. Otherwise, 300 students would wish to take the course, and everyone can follow the recordings on YouTube, obviously. So we limited to 100 students, and there are multiple courses in iLearn, as you may have seen, that link to this course. And it's from various degree programs. They all link into the main course. And this is the main course, the AIX BM4. And you can only take this course for credit if you have joined this course. You're unable to join the course now because the course is closed. It's capped to about 100 students. And you're most happy to follow the lectures or the recordings, but don't sign up for a seminar presentation if you're not registered in this course, because later when seminar topics get registered, Horst and I will check that only students who are enrolled in this course can actually sit the presentation. And the course also says, if you have joined this course and you see this message, then you can take this course for credit, and the admission was first come, first served, and it's 100 students at the most. Here you can find the recordings from last year in YouTube, and later today, when the first recordings are done, I will also paste the link to this year's recordings. But the recordings will be probably not too different from last year. Now, before Horst continues, I'll quickly ask you if you have any questions on the organization of the course, and if there's anything or whatever concerning a course that you may wish to have answered. If so, maybe just raise your hand or turn on your mic or send this in the chat, and we'll be most happy to answer your questions. And there's one student who asked, if you are in this iLearn course, you can take the course for credit. Yes, exactly the one I have just streamed, and I'm sharing that one again in Zoom via a link, that there's no confusion. You must be in that course, and that course says you can take this course for credit once you have joined this iLearn course. And if you have joined it, you can take the course for credit. We wish we could examine 300 or 400 students per semester, but Horst, I guess we're unable to do this, right? But everyone can follow the lectures and they will be on YouTube. Now, before I pass the floor to Horst, I'll say a few more things. There are lots of news around quantum computers on the internet. And the news are from something like quantum computers would not work to the other extreme that quantum computers would end the world. From my perspective, that's total nonsense. Quantum computers will not end the world. Quantum computers are helpful for a certain amount of computational problems. We will discuss this in a few weeks, but they will not help us to speed up every possible computational problem, and they will not turn evil, they will not start a world war, and they will not become super intelligent on their own. But you read this kind of stuff on the news, and then people, so-called experts who have a background in policy, but not in science, they write articles on the internet that quantum computers were more dangerous than AI and we should regulate all of this. Well, we don't regulate computers, so I don't think we should regulate quantum computers, rather applications. But it's sometimes just surprising the kind of stuff you find on the internet. Once we have built a framework of how quantum computing works and we look at concrete quantum computers, we will obviously also look at the theoretical boundaries of quantum computers. It's something that will only follow in a couple of weeks, and you will probably see that quantum computers are not dangerous. Quantum computers, however, they have some consequences. Yes, we can do certain computational problems faster. We've seen Grover's algorithm, which can lead to a squared speedup, but there is another problem for which we can get a near exponential speedup. Concretely, prime factorization. So if you have an integer and you want to know what's its prime factor, so it's the product of two prime numbers, this prime factor decomposition is computationally very difficult. And that's good because most of modern encryption is based on the fact that prime factorization is difficult and takes a lot of time for large integers. With the so-called Shor's algorithm, we can do prime factorization almost exponentially faster. That means once quantum computers are available on the market with more qubits and that work more reliable, today's encryption will end because you can just crack encryption and much faster than today, in fact, almost exponentially faster. IT vendors have obviously recognized that difficulty, and that's why lots of IT companies like Google, IBM, and others are working on something called post-quantum encryption. These algorithms cannot be cracked efficiently by a quantum computer. And this is a discussion that has been going on for the last 5 years or 5 to 10 years, and companies have worked on it. And they have proposed different algorithms. Some of them looked promising, while others were found out they couldn't be cracked with a quantum computer efficiently, but with a traditional computer, they could have been cracked very easily. So that's also not good. And it was also argued that one of these candidate algorithms was in fact proposed by the NSA with a backdoor. So they hoped it would go through and they could finally crack those supposedly post-quantum encryption safe algorithms. This has made progress in the last few years or in the last few months. And there is NIST, which is the National Institute of Standards and Technologies in the US. And NIST is a standardization organization and brings together lots of experts in working groups. And eventually they converged on 3 post-quantum encryption standards that are safe. It was reviewed by lots of experts, went through lots of working groups, and these 3 standards have just been released in August. So I had already created the updated slide deck in July, just when the summer break started, and then disappeared in the news on August 13, and so I updated the slides again during the summer break. So this is some progress, and now IT vendors have to adopt to these post-quantum encryption standards in the coming years, and step by step replace our traditional encryption with these new standards. So once more powerful quantum computers are available in the coming years or decades, today's encryption will have been replaced, and we're still safe, and we can rely on encryption. There's another book chapter. So when you see the iLearn course, it refers to my Nextcloud directory where you can find these slides, but also other things. And there's a book chapter. It's called Quantum Technologies. This book chapter was written by Daniel Akenine. He's one of the CTOs of Microsoft, and he's one of my friends. And he contributed this book chapter to one of my books a few years ago. And it's like 10 pages written for executives or decision makers making the field of quantum technologies more tangible. It's not just quantum computers, also covers a few other things like quantum sensors. And in fact, all of you use quantum technologies all day long because we all use USB sticks or flash drives. And for flash cells, you actually need quantum effects that they work. Otherwise, without quantum mechanical effects, we wouldn't be able to have flash cells. So we all use quantum technologies all day long from the first generation. And this book covers more the second generation, like quantum computers, quantum sensors, and so forth. You find the book chapter in the Nextcloud directory, and please read it. It will provide you with a few insights and prepare you a bit for this course. And I just wrote a new book chapter myself, which should also be available in the Nextcloud directory already. And that book chapter is called Quantum Computing: Foundations, Opportunities, Challenges, and Applications in Healthcare. It's for one of my new books that is just with Springer, and it's getting typeset and processed by the publisher. It's a book about healthcare where I'm one of the editors. And I wrote a chapter about foundations, opportunities, and challenges of quantum computing. And the healthcare part is probably just 1 or 2 pages or something. So it's more about an introduction to quantum computing. And on about 10 pages, I describe the essence of quantum computing, some of the maths, some opportunities, challenges, foundations. And we'll look into all of this in this course. So if you want to have a good preparation for this course, maybe read these 2 book chapters, and then step by step, we will explore all of this in the coming weeks. I had also sent you an update in iLearn about next week's lecture. Next week's lecture is not on Friday because next week, Friday, I'm chairing a hiring committee, and hiring committees for new professors, they typically take all day. So I'm unable to teach the lecture next Friday. But we will do the lecture next week on Thursday in the afternoon via Zoom, concretely from 4:30 to 7:30 p.m. I had posted this just before in iLearn. If you have time, join the live stream. If you don't have time, just watch the recording, which will appear on YouTube. And the lecture today and in 2 weeks and so forth are unaffected. So this only concerns next week's lecture, in which I'm simply not available because I need to chair the hiring committee. And with that, I will pass the floor to Horst, who will provide you a bit of his introduction on things like history, comparison to traditional computing applications, business potentials, and he'll set, I guess, some kind of roadmap for what we're going to explore in the coming weeks and months. So, Horst, the floor is yours.
Yeah, thank you, Patrick, for the introduction. And dear students, welcome from my side to our elective on quantum computing. My name is Horst Kunert. I'm since 20 years now at Technion Institute of Technology. My professional background is computer scientist and human biologist. That means I have a background in healthcare and in medicine. And I was CIO in a hospital and then in our university. So I planned and I built computing centers. My interest to quantum computing comes from a lecture, operating systems and computer architecture. And I used to make the students a gift to Christmas. So my Christmas lecture since 2009 was every year a brief overview on the technology on quantum computing in the field of operating systems and computer architecture. And since these long times, I can see that there are a lot of technical changes in the field, new approaches to quantum technology, to the hardware implementation, and a lot of companies working in that field. And that's the information that I want to share with you in my part of the lecture. Patrick has the major part of the lecture, but we will meet personally in January, and don't hesitate to ask questions regarding potential topic for your seminar paper or seminar work, but we are sharing the lecture in this way. So I now want to share the screen. So now you should be able to see my slides. So what are the topics I want to share with you this afternoon? Some fields of application, as Patrick already said, we use every day quantum technology, and from the business point of view, 1/3 of our world gross domestic product is made on the basics on the foundations of quantum computing, especially in the field of computer technology like laser, USB sticks, hard disk devices, and so on. But quantum effects already happened since many years, millions of years directly in nature. So what are the fields of application? We want to touch that field. Some physical basics or foundations in physics, some words on algorithms for quantum computing and the current state of development, and some hints and suggestions for further reading. So the fields of application of quantum computing are very wide. So if you want, we can call quantum computing a kind of enhancement in the field of Neumann architecture. What is the basis of all computer hardware, classical computer hardware that we use today? And the extension is built on parallelism. That's the field Patrick will introduce in several lectures, because this massive parallelism is one of the key specific topics on quantum computing. Quantum computing is very good in the solving of optimization problems and to code safer systems. Patrick already introduced the developments of the quantum, post-quantum cryptography, and the new recommendations from the National Institute of Standards and Technology. We also have a white paper of our Bundesamt for Sicherheit in the Computertechnik, our Federal Institute of Computer Security. According to the miniaturization of the components, even in classical computers, we sooner or later come into quantum effects. So the smaller the miniaturization gets into the hardware components of CPUs or other digital components, the more quantum effects could arise or can arise. So that moves us directly to a quantum world. And as we will see, or you will see during the lecture, the quantum world is an extension to the concept of the binary world of the classical computing system. Generating random numbers is needed in a lot of scientific fields, let it be computer science or data security or whatever other fields. So the true random generators are solved nearly by quantum computers or quantum computing, or the factorization of large numbers, matrix calculation, and so on. Nowadays, we have a topic or field, application field in machine learning, and the research in medicine and molecular biology, especially genomics, can be supported by quantum technology. Let us start a bit with fundamentals of physics, and I want to drop some names that are important in the development of the quantum technology that we see right now. So Isaac Newton, 1672, a British scientist, made up his thoughts about the topics of light. What is light consisting of? And Isaac Newton stated that light consists of particles. Then another Dutchman or a Dutch scientist, Thomas Young, an English scientist, Thomas Young, found out that light is a wave. That, what is it? What is right? Is light consisting of particles, or is light consisting on a wave level? Today we can say light is both. It is particles and it is wave, as a waveform. Another important scientist in this field was Max Planck, a German scientist working in Berlin. And he laid the basis of quantum physics. And he was working on the dual character of light. And he gave us the insight into the smallest parts of our universe, the so-called microcosm. And therefore, according to his name, Max Planck, the Planck's quantum of action, H abbreviated, is based on his final work. And Planck also did research on the wave-particle duality or dualism. A next famous name come into the play with Albert Einstein, who set the theory on quantum theory, especially on light. And he found out that the photoelectric effect is one of his basic works and his famous works. And maybe you know the photoelectric effect is the physical basis on all the photovoltaic fields that we have right now in our world to do the energy change and the energy transfer more in a green energy. So the photoelectric effect works on surfaces and produces electrical current. Albert Einstein got the prize, the Nobel Prize for the theory of relativity, but the major work was on the photoelectric effect as a basis for his quantum theory of light. Einstein was a bit careful with the interpretation, what he found out. Therefore, together with Podolsky and Rosen, he formulated the so-called EPR paradoxon or EPR explanation, and it has to do with a distance with the distance effect on the quantum physics. And we will show and explain it later on what are the locality or non-locality effects, and therefore the EPR explanation is one of the things Albert Einstein worked on. Another famous name in the field, maybe you learned about Niels Bohr in his atomic model in school. And Niels Bohr was one of the scientists working on the atomic model, and he worked on the Copenhagen interpretation of quantum physics. Niels Bohr was always a bit hesitating in accepting all the results of the quantum theory, which is mainly based on mathematics. It's more a theoretical work, but nowadays we have practical implementations of that was these scientists found out. So Niels Bohr, a famous word of Niels Bohr was, anyone who is not shocked by quantum theory has not understood it. And I hope after this lecture with Patrick and me, you will have more insight in quantum theory and in quantum physics, and you understand how quantum computers are built of. Another famous German scientist, Werner Heisenberg, did a lot of for the mathematics of quantum mechanics. He uses matrices, and he is also the creator of the uncertainty principles, what we learn later on. Some additional names: Erwin Schrödinger found out, an Austrian scientist found out the so-called Schrödinger equation of the wave function, and one famous picture to explain a bit the theory and the concept behind quantum theory is the experiment of Schrödinger's cat. And in his later years of his scientific career, Erwin Schrödinger worked mostly on molecular biology. That's interesting because he came from a completely other direction from physics, but at the end of his scientific career, he produced and published a lot of paper and work on molecular biology. Another name that you should know is John Bell from the Bell's laboratory. He worked on the inequality and entanglement and the local realism. So that was a bit in conflict with the EPR explanation, but Bell's uncertainty law is very famous in quantum technology. Another name, Hugh Everett, he created an interpretation of the quantum theory or quantum mechanics. He called it the many worlds theory. And you can see, and that was the first book that Patrick announced. It was about the metaphysics or the background or a meta perspective on quantum theory. So quantum theory and quantum mechanics is real. It's working in the microcosm that surrounds us, but as humans, we are living more or less in the macrocosm. Therefore, we don't have any senses for microscopic effects that really take place in the microcosm. And therefore, it's a bit hard for us to imagine all the effects of the quantum mechanics or quantum theory. In recent years, one famous name, Richard Feynman, who worked on the quantum field theory, and he was one of the founders and the producer of the first ideas how to implement a quantum computer. Then a very famous name from Austria, an Austrian scientist, Anton Zeilinger. He won last year the Nobel Prize for his work on quantum teleportation. So it had nothing to do with science fiction enterprise, Captain Picard. So Anton Zeilinger realized a quantum teleportation. That means a state of a quantum system to transport it via a fiber or via lines to use this entanglement. Carlo Rovelli, an Italian scientist, works now on quantum gravitation, and another very promising field, how to explain a bit how quantum effects are working in theory. So the fundamentals of physics try to combine always things or developments that are working in parallel. So, you know, from school, we have electrodynamics, we have magnetic effects in physics, we have electrodynamics. So quantum mechanics is a combination of electrodynamics and magnetodynamics. And therefore, we have another natural effect called gravitation, and new recent researches are done by Rovelli in the field of quantum gravitation. All parallel follows the theory of strings, and a new word or a new term in the field of physics is cubism. to indicate that it's a combination of various scientific fields in the field of quantum fields. In the beginning of my part, I said we are surrounded by quantum effects in nature. So if you imagine a photosynthesis is done by so-called antenna proteins in nature, or quantum lights in the deep sea. Maybe you saw some pictures, or the sense of orientation in the bird flight. Some call that the quantum compass, where birds find their way over the whole world. Cell communication on the smallest elements in our body, or brain functions, are explained through entangled neurons, and our sense of smell can be explained with quantum effects. So quantum effects are surrounding us at every time. So we are living in a world of quantum effects. And another applications in technology that was first started in the 1940s, 1950s, are scanning tunneling, microscope technology to learn on the structure on very small levels, or what we use daily worldwide in medicine are magnetic resonance imaging technologies to see inside our body, to see structures of our body, of our brain here, for example, or to find out the location of tumor cells. And a lot of applications in medicine are based on quantum technology. So the superconductor or transistors using quantum effects already. And in a German city of Essen, we have superconducting elements to transfer electricity over a distance of 1 kilometer. So you can see applications are all around us, and we have to look closely to these technical developments, and mostly they are on the basis of quantum theory. So again, some quantum or physics basics. The starting point of quantum physics was more or less on the theory of light and substance. So people always wanted to understand how what is light? Is light a wave, or is light a particle, or how is the substance built of? So the early Greeks found out or built up a model that substance is built of atoms. So this atoms term goes back to the old Greek scientists. But nowadays we know atoms are made of three basic components known as subatomic particles, consisting of protons, and protons have are positively charged. They consist of neutrons, they have no charge, and electrons. Electrons are negatively charged. And all these parts form an atom. So we have effects on the microscopic scale, and later on we will see these changes of the energy levels in the atomic field. So three basic principles you should know and understand if you speak, and we speak of quantum physics. So first of all, we have to understand the wave-particle dualism. I try to start that with the discussion: what is light? Is light a particle, or is light more consisting on waves? Or how behaves light? Then Werner Heisenberg stated his uncertainty principles, and Wolfgang Pauli, also a famous German scientist, stated the Pauli principles. So the processes at this level of atoms or of substance building blocks and never take place continuously. That's the main difference between our physical world, or our world that we live in as humans, that we have continuous changes of development or changes of speed, whatever. So our limitations are coming more from the classical physics. So in the world of classical physics, we are completely predictable. We can do predictive on the way how a bullet flies, how a rocket flies, or whatever. So the NASA can calculate with high precision the location of a satellite or a rocket within a billion of kilometers away. Think of Voyager 1 or Voyager 2. So the landing of a spacecraft on Moon and on Mars is only possible if we use the classical laws of physics introduced by Galileo or Isaac Newton. But that is not true for the quantum world. If we are working on the or looking at the scale of an atoms, the things are completely different. And that's the way we want to see in the next slides. So on the field of, on the level of atoms, or in this, sorry, in the microscopic way, it's working on discrete and indivisible, discrete, not further divisible packets. And these packets are called quanta, and plural, or quantum in the singular. This image shows very well the differences between the macrocosm where we live in, so it is a steady, continuously change, or in the microcosm where we use, we have the image of the changes of system more in steps, more in discrete steps like these quanta. That's a very good image to introduce the differences between the two ways like nature is or nature behaves. So coming back to the introducing question, what is light? Is light now a particle consisting of particles, or is light behaving like a wave? If we with a pistol on a screen, the bullets with this the famous double slit experiment. If you imagine you shoot bullets on this double slit wall, then the bullets fly to the one slit or to the other slit. So we have a typical pattern of particles. On the yellow screen, we see the bullets, they came through slits on the left-hand side, and the bullets came through to the slits on the right-hand side. If we use light and electrons using the same experiments, light behaves like being a wave. And we see this stripe pattern on the screen, on the reflective screen. And therefore, we could have the opinion light consists or is a wave, or consists of waves. On the other hand, if we use an electron beamer, and we use the same experiment with a double slit, slit A or B can be closed, and the electrons fly to slit number A or slit number B, and the pattern is exactly the same like using a bullet. So electrons are particles. So what is right now? In quantum physics, both is possible. Light behaves like a wave, and it behaves like particles. It depends on the energy of the light, and therefore the photoelectric effect that Albert Einstein found out is only true with ultraviolet light, not with visible light that we are surrounded by. So this photoelectric effect only takes place if it is ultraviolet light, but a part of the sunlight is always ultraviolet light, and therefore photovoltaic cells and fields are working very well in nature. Another interpretation that was done by Takamura was shooting electrons on through a slit on a reflective screen, and you see directly the interference pattern, and using different numbers, amounts of electrons. So the above picture has 200 electrons 6 electrons, number B. Number C is number B is 200 electrons, number C 6, and number E here we see directly the interference patterns of the electrons of this experiment. So the wave-particle dualism that Max Planck found out that the radiation or light consists of light quanta called the photons, and the energy of this photon increases with its frequency. There are some other scientists who made experiments on this field. A French scientist, Louis de Broglie, made a double slit experiment, and even in the 1990s or 1980s, they were repeating these experiments, and still nowadays it is one of the basics of a study in physics to repeat these double slit or these slit experiments. And we always come to the same conclusion: light is both. Light consists of a pattern of particles and as well as wave, and therefore Max Planck called it the wave-particle dualism. So what about measurement? In computer science, we always want to have a deterministic result. 1 time, 10 times, a million times, and we always have in a deterministic system the same behavior and the same results. In quantum physics, it's a bit different. So Werner Heisenberg said it is in principle not possible, impossible to give both the place and the momentum at the same time. That means to measure the momentum or the speed or the speed of a particle like an electron or an atom or photon. So we have to decide to measure speed, but never to the same time. So that is very typical to measure the outcome or to measure the result of quantum computer or quantum system. So it's also to understand that, and it is called the Heisenberg's uncertainty principle, that you cannot measure speed or spin or energy or momentum or location of a microscopic at the same time. So, used to have fields given out by Newton or by Galileo. So this is not a physical world, and therefore, again, it is not possible to determine the location and the velocity of a particle, of an atom, of an electron, of a photon, really at the same time. And therefore, the physicists and philosophers had problems in understanding the consequences of that rule. Therefore, are there non-locality effects or non-decidability effects? And that blows our mind a bit because we are normally in the world, if we take an apple or a stone and let them fall, it will definitely fall to the ground or to the carpet. And therefore, that's no longer true in the world of quantum. And therefore, we have to decide what to decide. What do we have to measure, and with what technology we want to measure the effect? So Wolfgang Pauli, a German scientist, also found out that 2 electrons can never be on the same physical state or never be on the same energy levels in these atomic surroundings. And the state can be given by the location or by the momentum or energy or spin. So we have a lot of possibilities to measure in the microscopic world, but we have to decide what to measure. So a particle cannot be where another particle is already, and that's the explanation. And if you want to try it, to walk through a wall, you will make up your experience for your own. You can make your experience for your own. you will get hurt. And therefore, that's one of the explanations that it doesn't work to apply the rules in quantum theory in our real world. And the explanation is even on the microscopic level true. Two electrons or two particles can never be at the same time in the same physical state. Therefore, walking through a wall is not possible and it's not feasible. So Richard Feynman, I dropped his name already, found out, a very famous physicist from the US, found out in 1982 that the quantum mechanics could be used to build a quantum computer or to calculate with quantum states. So he worked on radioactivity, on chemical combinations, and found out that electrons can be in several states at the same time and some states. It is called superposition. That means at that specific moment, only working in the microscopic, in the microcosm world, superposition exists. That means electrons have several states. So let's try to understand that. In a conventional computer with an 8-bit register, you have 2 to the power of 8, 256 different states. In a quantum computer, working with superposition, you have 256 multiplied with 250 states at the same time. And that's the quality of a quantum computer. The use of superposition. Later on, we will explain how could be superposition reach in a quantum system with 2 electrons or with 2 atoms as well. So to explain a bit, in the qubit system, we have several link states. And if we use the atomic weight or the amplitude or the spin, it depends on the measurement or on the system, what is used. So with a quantum system, we can have a lot of states in parallel. And that's one of the chances that we can use when we take a quantum processor, a quantum computer for our calculations. Not even with atoms or with electrons. So subatomic levels are everywhere. So water molecule, we can use a specific angle between the bonds, and they are exactly 107 degrees. So if you want, water is a kind of calculator, and we can use molecules, as we can see later on by nuclear magnetic resonance, can be used to calculate. And therefore, we have a lot of various approaches in implementing computers. And therefore, we can use molecular computers as well. But now we want to focus more on quantum effects. So I already explained that it's for us as in the classical world, or we are trained more in our schools or in university to live in the classical world. We have some paradoxes in the quantum mechanics that's a bit hard to understand. Remember the statement of Niels Bohr with the spooky effects, sometimes called, of quantum physics. So Erwin Schrödinger tried to explain the superposition, physical effect of the superposition with his image of Schrödinger's cat and Heisenberg's uncertainty principle we already know now, Bell's non-locality principles, and Hugh Everett with his many worlds principle or many worlds law. First of all, Erwin Schrödinger. So imagine a cat, a living cat is in a closed system, and you cannot see from outside into the box where the cat is. So you cannot decide, is the cat living or is the cat already dead? And inside the box is a specific mechanism that's working with radioactivity and poison will be brought into the box with a hammer with radioactive fall strikes at the glass bottle, and the poison will be freed, and the cat will die after radioactive activic systems. So from outside view, you cannot decide, is the cat dead or alive? You have to open the system. And opening the system can be explained in you have to measure the system. So in this specific time, when you are not able to decide, when you are not opening the box, is the cat in a state of the superposition? That means the cat is both dead and alive. A bit hard to understand, but fortunately, Erwin Schrödinger did not this experiment with his real cat. He was a cat lover, and therefore don't be afraid of the cat. It's only a thought experiment. So to explain the statement of superposition. Local effects. So if you roll a ball on a ramp, or if you let an apple fall or a stone fall, you have a directly a local effect, though the effect can be measured directly or seen directly. In quantum physics, we have the system of the specific effect of entanglement or superposition, but what we can't see. I already said we don't have any senses to understand quantum effects. We can see it, we can smell it, we can touch it, and therefore we are only able to see or to know about quantum effects with physical or technical systems. Bell said a classical local theory cannot explain the non-locality of quantum systems. And that was the problem Albert Einstein and some other scientists always had with quantum theory, that we have this entanglement. That means we have an effect on a quantum system. The quantum system can be miles away, kilometers away, with a great distance, but the system works in combination, and that's called entanglement. So famous mathematician Bertelmann said and wrote a book on that. If you have two socks, a simple example, and a red sock and a green sock, and if you see directly, if you have a look at one sock, at the red sock, you know immediately that the other sock you can't see directly must be green. But it is important to understand that the both socks have to be entangled. That means at one place they have to be together, and you should know what the two colors are. And as far away as the two socks can be, you know instantly what's the color of the other. That's something a bit easier explained, the non-locality principles where entanglement is used for. And entanglement is one of the specifics in quantum computing that is used in cryptography, and therefore quantum systems work with entanglement. And one of the famous scientists that first of all created this entanglement of two photons, two electrons, was Anton Zeilinger, the Austrian scientist working long at Innsbruck University, then at Vienna University, and Anton Zeilinger became or got a Nobel Prize winner last year for his foundations on quantum physics. So I've read many worlds. I don't want to get too philosophical in that point. So Everett had a new interpretation on quantum mechanics, and he called it a multiplicity of possibilities. So in a quantum decision, the world, as Everett says, splits into a multitude of universes, so multi-universe in his scientific work, and every action of one particle with another creates a new world. So each of these worlds, everything are identical except the selection made. And after that, the worlds develop in different directions. So it's a kind of meta theory, as it is called in science, and therefore it's interesting that a lot of scientific science authors or used that worlds that a picture of a multiverse in order that we have parallel universes, but we cannot prove that at all. It's a very nice theory, but please remember there are a lot of philosophers and physics working on that field in the many world theory. So let's go a bit back to real physics. So in the classical world or in the quantum world, there are differences between a classical bit and a qubit, a quantum bit. So the abbreviation of a quantum bit is a qubit. And we will use the term during the lecture. And we use this massive parallelity in the quantum world. So again, 8-bit or a lot of parallel states can be reached with a quantum byte or a quantum qubit. Here again, some differences between the classical bit and the quantum bit. So to explain the various states of a quantum system, there is used a sphere, the so-called Bloch sphere, but Patrick will explain that to you in detail in one of the next lectures. So here again, the differences between classical bit and qubit. A classical bit can be 1 or 2, and a qubit can be various states between 0 and 1, called ket0 and ket1. So we can go a bit through on that. So how to apply an algorithm for quantum computers? So remember, we use the state of a superposition of electrons or molecules or various states. And here with the superposition of 3 qubits, we see here this picture of various states. Then we apply the algorithm. We will answer the question today. How could an algorithms be applied on a quantum system? And the application of an algorithms could be via a laser beam, could be with microwaves, could be with electricity. There are a lot of physical technologies how to apply a quantum algorithm on qubits. Then the superposition after the algorithm is in our quantum system, in our quantum computer. So the next problem is how to measure the output. And in some implementations, you need hundreds, thousands, even millions of measurements to find out what is the real output of a quantum system. And as I already said, we don't have a deterministic system. So we have a system where we have to measure and we see with a certain probability that we found out a right output, the correct output. To imagine a bit how a quantum computer works, maybe you know from statistics in school or in university, a Galton board and a quantum computer calculates all the various ways and branches simultaneously. So that's a good image, a good picture, how to understand how a quantum computer works. And we have a certain probability to find out the result after the measurement. So the first algorithms for quantum computers were developed by Richard Feynman or Shor or Grover. So in detail, Patrick will show you how these algorithms work. So in the first time or the first ideas how to use or what to do with the quantum computer were we can use it for searching. You can use it for solving the factorization problem. And that indeed were the first algorithms that were artificially worked out for a quantum computer. Even a quantum computer was not available at that time, and we speak of a time in the 1980s, in the 1990s, where scientists, physicists, and mathematicians, computer scientists thought on the first way how could an algorithm look like. Two names that you should know in the field is Peter Shor from the Bell Labs, 1994. He was the first one who created a quantum algorithm for prime factorization. And the next one was Love Grover from Bell Labs as well. 1997, he created a search algorithm for n elements. So again, a comparison of quantum computer and quantum classical computer. So in a classical computer, we use a circuit model with logic gates. We are used to have this AND gate, OR gate, NOR gate, whatever. So it's based on a classical universal Turing machine. And a classical computer is more or less a general purpose machine. In a quantum computer, so that was my Schrödinger's cat. In a quantum computer, the mechanical solution is part of the algorithm. So we will see an implementation of the Shor algorithms based on molecules. And maybe today we are coming more to the conclusion that the quantum computer can be a subroutine of a classical computer. So give me a minute. I want to give our Schrödinger's cat the chance to go out. And I can confirm this cat is real. So what are the basic laws for a quantum computer? DiVincenzo, David DiVincenzo, now working at Jülich, a very famous research campus in the northern part of Germany, developed some criteria for a quantum computer. So a quantum computer must be scalable, very important. A quantum computer should have the ability to initialize a state of qubits easily. What is easily has to be defined. It must have long decoherence times. That means that we have a long time to measure the results of a quantum calculation, a quantum algorithm. And there should be a universal set of quantum gates. Nowadays, we have a lot of quantum gates. The Hadamard gate, as an example, can be called one of the basic gates that are similarly the same, working the same as in a classical computer, but with the means of quantum technology. And we need a qubit-specific measurement function. So DiVincenzo's list is very famous in quantum computer technology, and therefore we want to think about how could an architecture model of a quantum computer look like. So we have a massive problem because if we have too much qubits, we always have the problem how long is the decoherence time of this system in order that we have time or find time to measure the systems. So the simulation of a quantum computer can be, because in a classical computer system, it is a universal computer system. We can simulate all problems that we can imagine, and therefore, of course, quantum computers will be simulated with classical computers. But imagine that we have a system with 50 qubits. That would be petabytes of data, and they are needed to simulate a quantum computer, and therefore that comes to limits in the classical world. So an architecture model of a quantum computer, how could it be realized, is always based on a physical quantum processor. And in the next slide, I will show you 6, 7 implementations that are nowadays competing in the way how to implement a real quantum computer. Then we need a system to control or extract the information, the results. Then, of course, quantum error correction, as we have in a classical computer. Error correction is one of the basics in network theory, in CPU design, and so on. We have a lot of errors in classical system, and therefore error correcting mechanisms really very well known in classical computing as well. Then we need a logical quantum processor, that means on the gate level or whatever. And on that, we could apply a quantum algorithm. So the quantum computer hardware is nowadays based on new or well-known technologies. So I start with non-magnetic resonance quantum computer technology. So as higher we climb in our list as new and modern is the approach for a quantum computer realization. The next thing will be an ion trap, then superconducting circuits, then cold neutral atoms, very interesting, semiconductor spin qubits, diamond qubits, and photonic qubits or photonic computers. Let's start with nuclear magnetic resonance computers. So this technology, I would say, is very old. In the 1980s, 1990s, we have developed that kind of technology, and the first implementations, how a spin qubit can be realized via this nuclear magnetic resonance. So we use static and oscillating magnetic fields in order to control the spin states of the atoms or the molecules. And for quantum calculations, we use a system of spin in nuclei of the molecules. So unfortunately, we need a really huge number of molecules in the liquid. Normally, these liquids or this glass contains 10 with the power of 18th molecules that are used to measure nuclear magnetic effects. So the advantage of these type of approaches, we can use room temperature. Remember the picture of the D-wave system Patrick showed you at the beginning of our lecture. D-wave uses very low temperatures, so minus 273 degree temperature that the system is working. One of the advantages or pros of the NMR technologies, you can use it with room temperature. So the implementation is easy in this glass system. You have this liquid with 10 with the power of 18 molecules approximately. Then you have a magnet that generates a homogeneous magnetic fields called B0 and along the z-axis in our liquid called S. And we have coils L1 and L2 on the XY plane that generates radio frequency pulses in order to measure the magnetization. So B1 is a magnetic field realizing 1 and 2 qubit gates with a specific amplitude, frequency, and duration. So we measure the system again with a radio frequency amplifier and a signal preamplifier. So we used in this system, there are hundreds of pulses sent in order to make these measurements. So very simple technical design, but it works. We know that very well from medicine that this system is working. The problem is the time of coherence or the decoherence time, and it is a very short coherence time. So the pulse sequence energizes the system, and the signal is amplified and analyzed. So with the pulsing sequence of the magnetic radio frequency, we apply the algorithm to the systems, and we calculate that by changing the magnetization, and that's the application of the algorithm to these nuclear magnetic resonance system. So the problem is, how long could we hold the coherence into these clouds with this huge number of molecules? And unfortunately, in NMR technology, the coherence time is very, very short. So we need a lot of measurements, a lot of tries in order to find out a result. One first implementation with NMR technology, because I said this technology was one of the first that was implemented in quantum for realizing a quantum computer, is a 7-qubit system with atoms of a molecular system like fluorine, carbon, and iron complex. And again, in the same system. So imagine in our glass bottle, we have these atoms, very high number of atoms, and spin is changed by the magnetic fields, and the spin aligns itself parallel to the magnetic field and can be influenced again by electromagnetic waves orthogonal to this field, and the result will be the factorization of 15 into the prime factor. So the result is inside these molecules consisting of 7-qubit systems. And for the measurement, we needed 800 pulses of radio frequency. The prime factors 3 and 5 can be read out as the output in the spectrum of this liquid. So the advantage of NMR technology, it is widely used in medicine. So we knew and we know all of that technology. We apply that in many fields. The disadvantage is it is difficult to scale. We have a lot of noise in the system, and the signal strength can be very low. So therefore, following DiVincenzo's list, scalability low, the coherence time low, it is not used for a approach in a quantum computer design. The next is ion traps. So in the time level, ion traps were developed in the 90s, especially Anton Zeilinger was one of the scientists working a lot on this field of ion traps. So what is an ion? It is an electrically charged atom that can be fixed in an electromagnetic field and can be trapped in that field. Therefore, it is called an ion trap. So the ions, again, are changed with lasers, with laser beams, or with a microwave pulse. And we can manipulate the energy levels of the ions, and therefore can use the system or the ions to calculate and to apply algorithms. In our picture, we see a system of 4 ions and therefore a 4-qubit system. So ion traps can be used for 1 or 2 qubit gates. Entanglement is very important. It can also be created. The decoherence time is a promising advantage in the world of ion traps. It is scalable, and we can use it with room temperature. So we don't need the very big effort to cool down the system to these very low degrees in other approaches. We know a lot of quantum optics and laser technology for the design of this type of computer. And the problem is the number of ions as we collect them in a chain after each other, and therefore the scalability is a bit limited. But today we have some companies working on that field, especially Quantinuum. It's a company in Colorado in the US, and they have first developed the H series of a quantum computer in 2020. And nowadays, the new model is with 56 qubits, and they say one of the most powerful quantum computer available already for industry and scientific research, and most benchmarked approach. But we have other companies working on the field of ion traps like AQ2, Alpine Quantum Technologies, or some German company, Electron in Siegen, or in the UK, Universal Quantum, or in Maryland. So there are a lot of approaches, and maybe you follow the links in the slides to check out the website of these companies. Very interesting how they promote their quantum computer approaches. The next thing, there is a next approach that is very well known in classical computer technology are circuit technology, superconducting circuits. So superconductors, they have always no resistance when being cooled down to 0 Kelvin. That's approximately minus 270 degrees Celsius. You know, in these specific low temperatures, technical systems show these superconducting elements, or these physical elements. So superconductors are called a pair of electrons combined with so-called Cooper pairs, and they can charge an electron in 2 times. It is called a Josephson junction, and it consists of 2 superconductors. They are separated with a thin insulating layer, a barrier. So these tunneling effects are working with that Josephson junction elements. So according to the quantum mechanics, the wave function of the particle in front of the barrier allows us that the system tunnels behind this very, very small barrier, some atoms thick, and the particle can tunnel in both directions, and that's easy that we measure behind that barrier, so we can do calculations and measurement easier in a system with semi or superconductors. So we can divide the systems up in metallic or ceramic classes, conductors. So other semiconductors use more strontium, ruthenate minerals, and today systems are working with temperatures of minus 23 degrees. So I would say in a more specific fridge, normal fridge, you can use that in order to cool the system for minus 23 degrees, nothing compared to minus 270 degrees. That means a lot of effort, amount of energy to cool down a system in that way. So researchers at Jülich and Münster in Germany working on that superconductor made on chemical elements. Here again, a picture of the superconductor approach. So you need an inductor and a capacitor. The current flows in that direction, and the system is controlled with microwave pulses. So the pros and cons are, it is possible to do a very precise measurement. We can calculate very fast. The problem is the cooling effect, and a lot of space, was more space that we require as compared to other approaches. IBM is working on that system, and they state on their website with the Condor quantum computer, they have realized a 1121 qubit quantum processor with semiconductors. But also other companies are working on that. So please check the website, because the picture is not visible very well, but IBM has a roadmap with quantum computing reaching more over the 2030 years, and they are trying to implement different technologies, but rising the number of qubits from approach to approach. Another very new approach is cold neural atoms. So it is similar to ions, but atoms are used in the way that are before ions in an ion trap. So we can call it an atomic trap. So can also be cooled and controlled with laser systems, and they bring the particles into specific states, and they can generate superposition. You know, superposition we need in order to apply algorithms and to have or to use this massive parallelism in quantum computing approaches. So cold neural atoms scale well. They have a very long coherence time. It could be in the area of seconds, the range of seconds. Positive, it is used by room temperature. They are stable, and the laser setup, it's one of the disadvantages, is a complex setup. Some companies in Munich work with the cold neural atoms. Some companies in Munich work with that approach. Planck Q, it's a startup in Munich around Technical University, and they say our processors use atoms in artificial crystals of light, the fastest way to scale and to have useful quantum advantage. So it's more in the in the surroundings of the Munich Quantum Valley. It's in Munich they try to build up a kind of quantum ecosystems to foster startups and to develop, encourage startups to work in the field of quantum computing. Another promising approach is semiconductor spin qubits. Semiconductor spin qubits. Semiconductor spin qubits are a very well-known and established technology that is used in classical computing as well. So, but we are going more to the nanostructures of these superconductors. The qubits are realized as single particles with a specific nuclear spin. And the advantage, as I already said, is we have the industrial technologies and we can scale that technology very well. One can use phosphorus, for example, to use these quantum dots or develop these quantum dots into this superconductor technology. So quantum dots are called a nanostructure based on semiconductors, more or less gallium arsenide, very well known in classical computing technology. The size of this quantum dot corresponds to the wavelength of the enclosed electrons. Therefore, we are in the microcosm world, we are in quantum world, and these quantum dots can be produced artificially. That's very interesting, that we are able to produce atoms like natural atoms with specific effects or specific advantages, like the creation of specific size, shape, or discrete energy levels. So it's a very promising approach, but same problem, always remember DiVincenzo's list. How long is the decoherence time in the system? So it can be realized with classical chip development technology. So the qubits are a set of quantum dots on a surface on a classical semiconductor structure. We have a static magnetic field that uses energy splitting, Siemens splitting, Siemens, another very famous name in the world of quantum computing, and the magnetic field can switch spin up or spin down, and it can use as an electronic spin resonance system. Here a summary on the semiconductor spin qubits technology. We have gate electrodes. We use these kind of technologies already, and we have various very thin semiconductor layers, and in these layers electrons are moving and can be controlled by microwaves. The pro is the stability of the system, and the semiconductor industry is very well established with all the processes. And one of the problems is we need very pure materials, and therefore the effort is very high in order to produce these semiconductor layers. And we need cooling again. Some companies refer to this kind of technology, so silicon quantum technology. In Australia, in Sydney, they are working on that, and they say they want to produce a 100 qubit quantum processor based on semiconductor spin qubits, and that should be available with an error correction by 2028. You see, a lot of work in progress. So coming a bit to the end of my slides and presentation for the technical implementations, a new approach, very new approach is diamonds used for qubits. So I always said diamonds are a girl's best friend. So diamonds are a scientist's best friend in this case. So it is called diamond qubits based on nitrogen vacancy. So this vacancy in an atomic crystal or in a crystal, in a diamond crystal, can be produced artificially. And a laser could control again this structure. The advantages, it is very small. It can be used by with room temperature. It is very small and compact, but the production line is complicated, and it is difficult to reach entanglement into this system. Some companies, but some companies are still working on that. Diamond qubits with NV centers, that is called nitrogen vacancy. Again, Australia, Quantum Brilliance. Then in Saxony, in Germany, Leipzig, SaxonQ. So our technology, some statements from their website, our technology allows miniaturization to the nanoscale without the need of vacuum or ultra low temperatures. So that's one of the biggest advantages. We provide high fidelity qubits based on SaxonQ generated diamond NV centers. And the next one, next center is around Ulm and Leipzig. And they say they have the world's first multi-qubit mobile quantum processor. And another startup is Diatope in Ulm, Germany. So please refer to the websites and look around the website, read the white papers, please, and see how technology is feeling. And the last implementation is our photonic qubits. So the technology behind is old, 1940s, 50s. We had the first implementations of a Mach-Zehnder interferometers. So interferometers are used in atomic clocks. They're used in navigation for airplanes. And the system is well known and very often used in technology or in physics. So what is the principle behind the Mach-Zehnder interferometer? The Mach-Zehnder interferometer uses something called a beam splitter. What is a beam splitter? It is a kind of glass or mirror. It's a partially mirrored glass plate that reflects one half of the light like a mirror and transmits on the other half like a window. Therefore, it is called a splitter, a beam splitter. In the photon model, a photon has a 50% chance of being reflected or transmitted. So we can use superposition and entanglement with these systems. Therefore, a Mach-Zehnder interferometer is one of the physical basics how to implement a Hadamard gate. So Patrick Klauner will teach you a lot on the implementation and the use of Hadamard gate. So this kind of technology is called linear optics quantum computing. Sometimes you will refer or read about photonic chips. So the photonic qubits are routing photons through fiber optic connections and connecting them with an optical component and photodetectors. So a technology that is used widely in technology, networking technology, and many other appliances, many other applications. So the photons can be transmitted and entangled. That's very important. So it is following the rules of chip design. You're familiar with that. It's known that these systems have a high stability. Scaling is a problem, and the problem is we have no memory function with photonic qubits. So, but development is going on in that field. So, QUIX Quantum in the Netherlands is working with that technology, and PsiQuantum at Palo Alto, California, is also working on that technology. A recent publication of a Chinese photonic quantum computer with 256 qubits was a bit shaking the community, the quantum community. And please follow the publications to Yuzhang 3 photonic quantum computer. It must be really outstanding results and speed that this quantum computer reaches today. Here's some information on that system. It is developed by university and Professor Jian Wei in the Anhui province. He developed with his team this computer. And the challenges are always a comparison of classical algorithms and an algorithm applied to this specific photonic quantum computer. And for boson sampling numbers, the quantum computer can solve the problems that another classical computer, needs 20 billion years more than this quantum computer. Yeah. That's always difficult to prove these results, but sometimes algorithms are developed specifically to show the effects of a quantum computer and the outstanding speed of a quantum computer. Patrick also mentioned the term adiabatic quantum computing, and he said there is a kind of criticism on this approach of an adiabatic quantum computing. So the question is adiabatic quantum computing a quantum physically quantum computer following the rules of Di Vincenzo, or is it a kind of other technology? And adiabatic quantum computer is implemented by D-Wave, a Canadian company Patrick also mentioned before. But adiabatic calculations are coming more from thermodynamics. That means there is a heat distribution between surfaces, and this adiabatic computing is very well suited for solving optimization problems and finding a global and local minima. Therefore, it is sometimes called an annealing process, and this annealing is used in other types of industries, like in the steel industry, to slow down the phase transitions by heating, holding, and cooling metals. So adiabatic computing is a typical form of an annealing calculation. So it comes more from the material sciences, and the first company who followed that approach was D-Wave in Canada. They use big cooling facilities in order to get this superconducting situation. And they use as well Josephson junction. The number of qubits they say they have is really challenging, but scientists come to the conclusion is not a universal quantum computer. It works with quantum physics, with quantum technology, but this is not a classical universal quantum computer, and therefore it is very well used, and a lot of research for these kind of problems solved with a quantum annealer. Other competitors of D-Wave are Fujitsu and Hitachi in this field. So use specific states of molecules to perform the computational operations, and they can store the data in their elements. And as other technologies, they use quantum tunneling to increase the speed of the computation. If we want to read more on annealing technologies, quantum annealing, so please refer to this publication here at this slide, or to other PDF files related to quantum annealing. So D-Wave was founded 20 years ago, and it was a kind of shock in the industry and in scientific world that D-Wave was sold to Lockheed Martin, and the NASA in 2030 opened a public resonance for the field of quantum computing with the promising number of 2,000 superconducting elements called qubits by D-Wave. So they made always competition with Google, and therefore they called it the Leap Quantum Cloud Service they have. So Patrick also told you that they offer a free time for use for using this D-Wave quantum computer. So summarizing a bit what we have learned today, the first implementations were indeed the nuclear magnetic resonance technology in the liquids. The problem is the scalability. The problem is that the low decoherence time. And you can see on the timeline that 1997, Nick Gershenfeld from MIT and Isaac Chung from IBM implemented the first quantum gate with 2 qubits, and they implemented the search algorithms for n equal 4. So the realization was atomic nuclei following this NMR model. The next time leap was over the year 2000. So 2005, the Innsbruck Anton Zeilinger constructed the first quantum byte. And the second kind of realization was an ion trap. I already explained what an ion trap is all about. And ion traps are still a technological line that is followed today by several companies, and even a promising approach. The third wave, or the third way of realization, was working on the superposition and working on error detection and error correction. And in the year 2004, Professor Zeilinger was able to do a teleportation of a quantum state over a distance of 6 kilometers. Today, these quantum states can be teleported by satellites or by fiber or by other transmission lines in order to use these cryptographic systems and to check the state of the cryptographic system. So 2011, it was possible to do an entanglement of 3 qubits. You see, there's a robust technology, and here are some examples of the first D-Wave system with 512 qubits. And today we have over 2,000 qubits in the D-Wave system. Google was always a strong competitor in the market. So Google, IBM, Microsoft as well, the really big ones in the field of the big numbers in the world of quantum computing. So the Cirq system of Sycamore produces or offers a library, a Python library, where you can use it in order to make your first steps in quantum system programming. 2017, we had quantum simulators and some prototypes in atoms and atomical optical grids. Yeah, the research centers mainly working on that were the University of Innsbruck or the Max Planck Institute at Munich. Garching can be named as the worldwide leading research institutes on that. 2018, Google announced the 53 qubit system. I don't want to go into much detail of the systems because it's now a little bit outranged. But at the same time, or 2028, the European Union started a project, Open SuperQ, with the goal of a 100 qubit system and an own quantum computer operating system. So you can see there is still a lot of work now going on now and in the future. Here's some images and impressions of the IBM 5-qubit computer in the cloud system. And it was a big surprise that in the year 2019, IBM announced that they go to city Ehningen near Stuttgart and to install a 27 qubits universal system that can be used for science. You have a chance to use this system. And yeah, it's working with low temperature and has 27 qubits. Here the according web links to the IBM Q system and some YouTube videos for that system. IBM also announced a quantum information science system, a kit, a programming kit, Qiskit, where you have a simulator and a library with some basic programs. So the next step or development or the next player in the game is Google with the Sycamore quantum CPU, and they have realized 44 qubits on a microchip, on a 1 centimeter microchip. So quantum computer simulation, it's interesting how much supercomputer, classical computer power you will need for simulating quantum computer with 42 qubits. And there is a really good article on that field. So it reaches the limits of our possibilities today. So for the simulation of 42 qubits in the supercomputer environment computing center at Jülich, you need around 300,000 processors with a performance of 1 quadrillion computing operations per second to simulate this quantum computed system. A few years ago, that was really outstanding, but nowadays with artificial intelligence, with computing centers with 100,000 NVIDIA graphic chips or graphic processors, that comes into reach into our line in order to do more work and more simulation on quantum computing. Here an image of the Google Sycamore system. And further players in the market are, again, Amazon, Honeywell, Rigetti, Berkeley, IonQ, I already mentioned that company, Yuzhang, China, and Xanadu in Canada, and some links to research centers Max Planck, and in Austria. Fraunhofer is very well engaged in the research in quantum technology in Germany. And here is a link for the European Union Quantum Flagship Program. A nice overview on the German quantum ecosystem can be checked in the Bitkom website. So in this Bitkom link, you will find a list, an address list of German companies. They are working with quantum or quantum systems, startups and established companies. Very interesting to look around who is the next company. So coming to the end, I want to give you a glimpse on the future on quantum computing, where it is needed, where you need competencies in quantum computing, and why do we engage as a university of applied sciences in the field of quantum computing. So there are a lot of domains where quantum computing is relevant. Airlines, banking, finance, chemicals, research, healthcare especially. So Patrick writes and wrote a book on that. Life sciences, the meta term for that, and especially research. So I think with these abilities and with this knowledge in quantum computing, you can offer a lot of doors in company if you have knowledge on how to work with quantum computers, how to program that specifically, and how to manage the transformation of some problems and research in quantum computer technology. So at the end, two interesting links where you can refer some basic terms in quantum computer. Quantum Atlas is very interesting, and quantumcomputing.ebm.com, where you can have access to manuals, to a simulator, and a lot of further reading and additional information for quantum computing. So that was from my side, and I hope you have now an overview on the implementation, how could be the design of a quantum computer. It's real. Quantum computers are real. It is a very fruitful field for startups. Maybe you think on that field. To do consulting in the field of quantum computing. So I think it's a very interesting field, and I never stopped learning in the field of quantum computing, and it's always a challenging subject for me, and I hope for you too. Thank you very much for your attention, and I hand over and I give back to Patrick.
Yeah, thank you very much, Horst, for your insights. We're done with the introduction chapter, and Horst will speak again in chapter 8 about quantum computers and programming. You will see some of what you have just seen, and maybe it will be elaborated a bit by Horst then, right? So what you see here is the agenda for the remainder of the term. So what we want to do is, and Horst mentioned, for example, the Harder-Matt gate. These are the fundamental operations in a quantum computer, like you have a NOT gate, an AND or an OR gate. In traditional computing, you need fundamental gates in quantum computers. For example, a Harder-Matt gate and others. Those will be discussed as of chapter 5, where we look at the fundamental gates and operations. We'll combine them to have algorithms. We will look at theoretical limitations of all of this and how to implement it in real life, write code and run it, in order to make it to the architecture chapter, in which we look at the fundamental operations of a quantum computer. We need to spend the first few weeks on the underlying maths. We need quantum theory, which is the very foundation of all of this. But in order to do quantum theory, we need to look how quantum systems work. And for that, we need the necessary foundations in terms of maths. And we still have like almost an hour left. So we will start with the foundations today and see how far we get. The good thing is, in order to follow this course, all you need to know are complex numbers and linear algebra. Concretely, we will start today with complex numbers, and then we will take linear algebra structures like vectors and matrices. We will also revise them, but we will eventually not use them just for real numbers. We will use them for complex numbers. And then we are working in complex vector spaces. But first, before we get there, and we need these complex vector spaces to describe our quantum mechanics and eventually our fundamental gates. Because when you look at traditional computing, what you work with is Boolean logic. And here we need complex vector spaces in order to build our fundamental gates. Complex numbers are the very foundation of quantum mechanics, and it's absolutely essential that you understand complex numbers in order to be able to reasonably continue with this course. And I want to know from you, maybe send me a thumbs up if you're okay with complex numbers, or a thumb down if you have never come across complex numbers, or if you just forgot largely about them. So please send your reactions here. And I largely, well, mixed responses, and that's absolutely fine because we will do a quick intro or revision to complex numbers and to the parts we will need in this course. If you have never come across them or forgot about them, spend a little bit of extra time on revision. And I mentioned these books before, like the Quantum Computing for Computer Scientists book. That one is key to this course. And what we do now in terms of the maths is also one of the chapter or two of the chapters in the book. And why do we need complex numbers? So if you have an equation like x squared plus 1 is 0, that's something we cannot solve with the set of numbers we have seen so far, because if you plug in, say, a positive number or a negative number and you square it, this will not be negative anymore. And then if you have something that is 0 or positive plus 1, this cannot be 0. So when we start with, say, increasingly more complex sets, like the positive numbers p, it's the integers 1, 2, 3, and so forth. We can extend this to the natural numbers, which is just the positive numbers, and we add one element, which is the zeros. And we can have integers, which are whole numbers, both positive and negative. This is often denoted as z, and it's the sets we have seen before, 0, or the elements in the set we have seen before, 0, 1, 2, 3, and so forth. But also the negative ones like -3, -2, -1, -1,000, and so forth. And we can further extend this when we get to the rational numbers, often denoted by Q, and these are fractions. They are all possible fractions where we have m divided by m, and m is from the integers, and p is from the positive numbers, because we cannot divide by 0. So we cannot put the natural, n needs to be from the positive numbers, not from the natural numbers. And since m is from z, meaning we also get negative ones. So rational numbers are all valid fractions. It's a set of all of them. And then we can further extend this, and we get to the set of real numbers. Again, we build increasingly more complex sets. Like you've seen, the natural numbers include all the positive numbers. The integers include all the natural numbers. The rational numbers also include all the integers, but we always extend. And so we extend the rational numbers further by saying we have the real numbers r, it's the rational numbers, and we add more numbers that we cannot actually describe in terms of fractions. Like the square root of 2 cannot be described by a fraction, or e, or pi, or many others like a fraction of e and pi, and so forth. So, because e divided by pi doesn't fall into here, because we said m must be from the integers and n from the positive numbers. But e and pi are both real numbers. So this is again a set of infinitely many real numbers, and that we're adding on top of the rational numbers. And this is the set of real numbers. But even the set of real numbers is not enough to solve this equation here, because if we say we have x squared plus 1 and we subtract 1, then we would have x squared is minus 1, but I cannot take the square root of a negative number. And we still want to be able to solve something like this. So we can introduce the complex numbers. I'll soon present more on the whiteboard, but just here briefly. So I say I have x squared plus 1 is 0. I can subtract 1 from both sides. So it's x squared is minus 1. And this doesn't work with the real numbers, but in fact, the solution is we introduce a new number I. And I is the imaginary number, and I is the square root of 1. Something we cannot describe with the real numbers. And then if you, for example, square I, so you say I squared, you square root, or you square the square root of minus 1, that means I squared is minus 1. And this is something we are unable to do with the real numbers. For this, we need to extend the real numbers and get to the so-called complex numbers. And we'll introduce them now. I'll switch to my iPad in order to do some of the maths with you. So we'll start with the complex numbers. And my handwriting is not too great, but all the stuff I'm showing to you is typeset on the slides or in the book. So that's more easy to look at for a revision. And we said, for example, x squared plus 1 is 0. We are unable to solve this with the real numbers. So we can say x squared is minus 1. And I've just updated my iPad to the latest iOS, and you see it automatically does some handwriting recognition here. I'll check later how to turn this off, because I just updated to latest iOS a few days ago. And if we then take the square root, we would have something like x is the square root of minus 1. And that's something we're unable to do with the real numbers, but we can introduce and say I, the imaginary number, is the square root of minus 1. And I squared, therefore, would be minus 1. That's just what we did. And now I'll have a quiz for you. And please don't check for the answers directly in the slides. The slides just contain this as a summary. We can say, or we can wonder, what is I cubed? You can think about this for a second for yourself. And we can actually now write this out. So I cubed is I times I times I. And we've seen that I squared is minus 1. So we say, well, this is I squared times I, because we just merged two of these. And I squared is minus 1. And we still have the I. So we can just say minus I. This is how you work with this imaginary number. And working with these imaginary numbers is sometimes something you need to get used to, and there are all sorts of tricks what you can do to make them look nicer. For example, something that really doesn't look nice is if you see a term that is something like I divided by, 1 divided by I. You would typically in your expressions aim that you put the imaginary numbers in the numerator, not in the denominator whenever possible. So rather put them at the top than at the bottom. And now we can wonder about how we can simplify something like this. It's fairly easy because we have our 1 divided by I, and we can just multiply the numerator and the denominator by I, each of them, because I divided by I is just 1. And I can multiply the fraction before by 1. And now I can simplify it. So 1 times I is just I, and I squared is, well, I'll just write it out. I squared is, as you remember, minus 1. That means I divided by minus 1 is just minus I. So always try to simplify something like this because it really doesn't look good. And I think minus I looks much more intuitive than 1 divided by I. And we got also the right suggestion a minute ago here in the chat. Now we will come to a proper definition of complex numbers. And this is something I will show you again in the slide deck. A complex number is, for example, denoted Z, and Z is defined as follows. Z is defined as A plus B times I. So this cross here is just a multiplication, just to highlight what this what BI means, but often it's just written out in short that it's A plus BI, which is B times I. And A and B are both real numbers, any real numbers. And A is often called the real part, and B is called the imaginary part. And I is just the imaginary number from before. And now all possible real numbers that you plug in for A and B respectively, this would eventually create a set of complex numbers. So it's also an infinitely large set. Sometimes the complex numbers are written in a simplified way, something like AB, and you put parentheses around it. Sometimes that's the way to just write complex numbers shorter, where A is the real part and B is the imaginary part. And I want to know from you now, and include you also here, and you can tell us in the chat, or you can just raise your hand or turn on your microphone, where you have come across complex numbers in the past, at least the ones of you who have worked with complex numbers already. If you have any suggestions where you have dealt with complex numbers, please tell us. One person sent a thumbs up. Feel free to turn on your mic and tell us more, or send us in the chat if you don't want to be using your microphone. We'll give everyone a short moment to tell us more. I guess there are more of you who have seen complex numbers if I compare to your answers before. So whatever you can tell us about complex numbers, please send it in the chat so I see what you have used them for, and then I'll provide some insights where they are typically used. But there are no answers in the chat yet, so we'll go ahead and waiting for your response. So you see complex numbers in certain applications in physics or electrical engineering or signal processing. We've seen here in the chat, now we're getting plenty of answers. One student says he has seen them for complex AC current calculations. Yes, that's why here electrical engineering, also for some problems in signal processing. One student says he hasn't seen a real use of them, but learned about their form. Okay, this is something that happens, unfortunately, quite often if you study computer science and in your first year in one of the maths courses, you learn about complex numbers, and something you would often see is how to, I don't know, build a class or implement a class in a programming language for complex numbers and various operations, and you create objects and you add or multiply these complex numbers, but you don't really see what they are useful for. In fact, there are some applications, even in computer science. For example, certain computer graphics operations can be described quite nicely with complex numbers as an alternative to other representations. There is also even an extension of complex numbers, quaternions. You can use them even better for certain computer graphics problems. In one application, which is the key of this course, is quantum computing. So I think the applications of complex numbers in computer science are limited. But there are applications, and there's more than quantum computing, for example, computer graphics. And we will now revise a few fundamental operations of complex numbers. If you have not seen them, this will be a tough introduction to you, but please take all the resources you have at hand in order to become more familiar with this. And I'll switch again to my iPad so we can do some calculations together. So we can start with addition of complex numbers. We can say we have a complex number C1, which is 3 minus I. So A is 3 and B is -1. We can have a second complex number C2, which is 1 plus 4I. And your task is now that we add C1 and C2. And what you're adding is you're adding the two real parts and you're adding the two imaginary parts. So if you have your result for adding C1 and C2, please send this to the chat and we'll compare if you're all on the same page. Get the first answer. So 3 plus 1 is 4. We have 4 minus 1. So 4 plus 3i, which is fairly simple because you're just adding the components. We can also do multiplications of complex numbers. For which we can just use the complex numbers from before. So we can say C1 times C2. And I will just write out these complex numbers again. So it's 3 minus I times 1 plus 4i. And in fact, it doesn't matter if these are complex numbers or some other elements. All you're doing is you're just multiplying these two parentheses with each other. So it's 3 times 1 plus 3 times 4i. It's minus I times 1 and minus I times 4i, and you sum this together. And I want to know from you what your result is when you sum all of this up. Sorry, when you multiply these two complex numbers and then you sum up all these individual products. Let us know what you got. I'll already do this now step by step. So it's 3 times 1 this is the first one. Then 3 times 4i. So 3 times 4i. We then have minus I times 1. So minus I times 1. And then the last one here, that's the more tricky one, it's minus I times 4i. We can all sum this up now. So this is 3 plus 12i minus I. And here it's 4 times I times minus I. So it's minus 4 times I times I. And you can maybe guess or any suggestions. What's this term here? There any suggestions from your side? This is maybe the more tricky part. It's plus 4, that's correct, because I squared is minus 1, and minus 1 times minus 4 is 4. So eventually we have 3 plus 4, which is 7, and 12i minus I is 11i. So we had the right suggestion here in the chat. There was just a typo by that student. Now we've seen the concepts of addition and multiplication. Now there is more we can do with complex numbers. There is the so-called modulus, sometimes also called the absolute value of a complex number. The modulus of a complex number is the following. Imagine we have a complex number z, for example. We want its modulus. That means we have our a plus bi, and to calculate this modulus, we take a squared plus b squared, and obviously we take the positive one here. So we can try this out for an example. We can say, for example, z is, well, we call it c for now, maybe. C is 1 minus I. And I want to know from you, what's the modulus of c? If you have any suggestions, please send this to the chat. It's the square root of 2. That's correct, because it is the modulus of 1 minus I. And I leave out this plus now, because we anyway just take the positive one. So it's 1 squared plus minus 1 squared. So it's the square root of 2. We'll do another c for now. It's 4 minus 3i. And I want to know from you what's its modulus. If you have any suggestions, send this to the chat, please. So this is the square root of 4 squared plus 3 squared minus 3 squared, but anyway. So this is the square root of 16 plus 9 is the square root of 25, and therefore 5. There is another important concept. It's the so-called conjugate. The conjugate of a complex number looks the following. Say we have a complex number z, which is a plus ei. The conjugate, you put a bar typically in the notation on top, where just changing the sign of the imaginary part. So this will be something like a plus bi will turn into a minus bi. This is the conjugate part. And I think if we look at an exercise, this would be fairly simple, but we will still try it together. Imagine z is 5 minus 2i. I want to know from you what is its conjugate. And if you know this, send this to the chat, please. There's a question about the conjugate sometimes being written like this with a star. That's just another way for the notation. So if you put the bar or the star, depends on the literature. We'll try using the bar throughout the course. But if you ever see a star, that's exactly the same. So I want to know answers from you. I said C is 5 minus 2i. And what's the conjugate? Please let us know in the chat. And we got the right answer now. It's 5 plus 2i, because we just changed the sign of the imaginary part. Now we can also do a geometric representation of all of this. Geometric representation. And we can represent complex numbers as vectors. For example, we can put our coordinate system here, and we can have a real part and the imaginary part there. And so we can represent our vectors as or our complex numbers as vectors. For example, I'll just try some example. We can have a complex number that is, for example, z is 4, or you can say 3 plus 4i. So 3 and 4. So C could be represented like this, that you have the real axis and the imaginary axis. And you can wonder about what happens if we apply the operation we have just seen before, the conjugate. Then we are just reflecting the vector at the real axis. So C bar, meaning the conjugate of C, is 3 minus 4i and would be somewhere down here. So this is the geometric interpretation of complex numbers, as well as the conjugate operation we had just seen. When it comes to complex numbers, there are far more calculations and things you can do. This was just the very basics. So this is not an intensive course about complex numbers, but we need to know what we are talking about. And there are two more things we need to do. So we've just seen addition and multiplication, the modulus, or the absolute value, which is in fact just the length of the vector from the geometric perspective. We've seen the conjugate, and we've seen the geometric representation in this complex plane where we had the two axes, the real and the imaginary axis. And we've seen this. And next, we will look at two representations very briefly, which we may need later in this course when it comes to some more complex operations in a quantum computer. We need the polar representation and the Euler's formula for complex numbers. Who of you still remembers the polar representation in the Euler's formula? If you do, maybe thumbs up. If you don't, thumbs down. We've just seen this one here before on the iPad, that we have the coordinate system or the complex plane with a real and an imaginary part. And we have a complex number that is a plus b times I. And we've seen we can represent the complex number here. We have an a component for the a and the b. And we've seen the length of this vector. And the length of this vector was just the modulus or the absolute value. Now, down here, you can put an angle between this vector and the real axis. And that angle is called theta. You all know how to calculate such angles from linear algebra. If you don't remember how to calculate this stuff, you can just look this up in the book. Probably you don't need to do this by hand in this course anyway, but the book can definitely be a reference for more details. And we can represent our complex number, which is a plus bi, which is exactly this here, a, because I said this parenthesis notation is just a different notation for a complex number. So a plus b times I can be represented, if you remember, linear algebra and also geometric functions like cosine and sine. We can say that this can be represented as r times cosine of theta, which is the a component. So that part here, it's r, the length of the vector, times cosine of theta. And the imaginary component is r times sine of theta. So just trigonometric functions. And this is the b. And obviously it's a plus b times I. So don't forget the I here. And you can just move the r out. So you can say r times this sum, and it's cosine of theta plus, and we move the I to the front in this product, I times sine of theta. This is just a different representation of complex numbers that comes with some benefits. Sometimes when you multiply or you do certain operations on complex numbers, you can do this quite efficiently here. And this part here, so cosine theta plus I times sine of theta, that one can be written with Euler's formula as e to the I times pi. And you're probably wondering, what does that mean? And remember, this is just the angle. This is r, the length of the vector. If r is 1, you would just put a 1 here or just put e times I to the theta. And I'll briefly switch back to the iPad. And I will ask you if you have ever seen something like this. E to the I times pi is minus 1. Who has ever seen something like this before, somewhere on the internet? Maybe thumbs up or thumbs down if you have never seen this. Give you a moment for more responses. So, some thumbs up, which is good. And what does that actually mean? If we go back to our coordinate system, so we have the real component here and the imaginary one here, say this is the coordinate system, we could have a complex number somewhere here. And this would be, say, C is just 1. Just has a real part, no imaginary part. And if I rotate this, and we rotate always anti-clockwise in geometry, we rotate by 180 degrees, which is just pi, because 2 pi is 360 degrees. Then we are here. And this one would be C is -1. So we could say this C1 and this is C2. This is a complex number, just -1, only has a real part, no imaginary part. And if you put all together what I've just shown you, and this one here will make sense. Because if I rotate a complex number by pi, meaning by 180 degrees here anti-clockwise, and I just had the original one, my C1, and I rotate this by pi, I get to -1. So e to the I times pi is -1. And this has all to do with this generic definition of, or with this Euler's formula, which is a different representation of complex numbers. So we've just seen, and I'll just go back that we're all on the same page. Slides are coming. So we've seen this polar representation, and we've seen Euler's formula, which is an equivalent. And all of these three representations are equivalent. If you struggle to work with such angles or the trigonometric functions, look up the book. It's explained in greater detail. In this course, as I said, you don't need to calculate this on your own. Probably we'll use computer tools if needed for some of these gates. But if you don't feel too familiar with this, look it up. Further reading is chapter 1 of this book, Quantum Computing for Computer Scientists. We have a little bit of time left for today to do a few more tricks around complex numbers. Just that you feel more familiar with them, and maybe there are some new insights for those who have done complex numbers before. Just switch to my iPad again. We can do some problems together, and you'll find also the solutions in the slides. We could try to simplify something like 1 plus I divided by 1 minus I. As I said, I don't really like having imaginary numbers in the denominator, so we can try to simplify this. So we can say 1 plus I is 1 divided by 1 minus I. And trying to simplify such stuff, has any of you ever done this before, maybe in your maths introduction or something? Because we have lots of students also from abroad taking this course. So maybe thumbs up or thumbs down if you have ever tried in the past to simplify such complex numbers. So a few have seen this. And if you have not seen it, it's perfectly fine. What I can do again is I can multiply this just by 1. And 1 is just 1 plus I divided by 1 plus I. Because this term here is just 1. It's just I divide something by itself, it's 1. But I multiply this from the right. And now I need to multiply these fractions with each other. And multiplying a fraction here with a different one means I multiply the numerators and the denominators. So what I can do is it's 1 plus I times 1 plus I. So this is 1 plus 2I plus I squared, because 1 times 1, 1 times I plus 1 times I plus I times I, so it's I squared. And this one here is 1 minus I times 1 plus I, so it's just elements. It's just the same rules you know from algebra. Whether it's a complex number or not doesn't matter. It's just elements. We're dealing with numbers or symbols. So it's 1 squared minus I squared, because it's 1 minus I times 1 plus I. So it's just A squared minus B squared. Now I can try to simplify this, because we see in the numerator, it's 1 plus 2i, and here we have this I squared, so it's minus 1. And in the denominator, we have 1 minus I squared. So I squared is minus 1 times minus 1. It's 1, so 1 plus 1. And we can try to simplify this further. The 1 and the minus 1 just disappears. So it's 2i divided by 2. So 2i divided by 2 is just I. So we see the term we have just seen at the beginning can be totally simplified. And there are 2 more that are a bit tricky, but it's just to quiz you for the last few minutes. Has any of you, before looking at my course, seen something like this? I to the I. Thumbs up or thumbs down if you have ever seen this until a few days ago before. So no one. And I have to admit, I also didn't see such stuff when I did my undergrad degree. I saw complex numbers and how to manipulate them, the polar form and the Euler's form. And obviously, if you have a proper introduction to this, you see more of it. There's other stuff you can do, like take a root of a complex number and such stuff, but we don't really need that for that course. But I haven't seen or I didn't see when I was in my undergrad, things like I to the I. And I started seeing such stuff a few years ago on the internet. There are all sorts of YouTube videos where mathematicians work with complex numbers and do some strange stuff. Even, I don't know, combine calculus on complex numbers, so do calculus on complex numbers and this kind of stuff. And then I've seen I to the I. And what is that? First, we need a brief extension of what we did before. We've seen before the Euler's formula, and we said a complex number z can be represented as e to the I times theta, where theta is that angle. It was just what we had seen here and before in the slides. And we have our angle, theta. And what we can do now is, and there's one person here who wrote in the chat, black pen, red pen. This is exactly the guy who does these kind of videos on the internet. And what we can do is we can apply, so we said Z can be represented as R times E to the I times theta. And we can apply the logarithm to this. And here I can apply the logarithm as well, which is R to the I times theta. The logarithm, so we can apply logarithms, in fact, to complex numbers. And now we can apply logarithm rules to this one here. We can say, well, this is the ln of the first element, R, plus the logarithm of e to the I times theta. And this, still the logarithm of R. And here, this is the natural logarithm, and we have e. So this is I Just wait a second. My pen stopped working. Just wait. And we will then we just move down this piece here, I times theta. Now, you wonder, what is this useful for? This was just an excursus which will help us to solve this one here. Because we can say I to the I is E to the ln of I. So this is just the I to the I. Because I've just, with the area I'm putting here in blue, I've just rewritten I, because E to the ln of something is just something. And then I still have this I here. And I can move this down to concretely here. So we can try this out. It's E to the I of ln I. Now I can try to simplify this further. I can try to move out the I, and I can say, well, this is E to the I times ln1, and ln1 is just 0, but you'll see soon why, plus I times pi half. It's a trick. There's one small step in between. You need to come up with your own, but with all the things we have just seen, you'll make easily this step from here to there once you do your revision. And then, so this is just a little quiz of how to do this exactly, but I'll leave this to you. And then this is 0, because before you've seen at the ln of a complex number, we've just done this before. So what we've just seen here applied to I, but this is your quiz, how to do that step. And then we see that this is I, ln of 1 is obviously 0. So that disappears. And then we still have this piece left. So I times pi half. Then we have E to the I squared times pi half. That means E to the minus pi half. Because I squared is just minus 1. And this is then something like around 0.20788, whatever. So you see, we can actually calculate I to the I, and I to the I is not a complex number anymore. In fact, it's a real number. And we can continue such stuff for the last few minutes for today. We could even try other stuff, like the ith square root of I. Also looks strange. I also didn't see this in my undergrad. I only started seeing such stuff in YouTube videos a few years ago. We can say, well, this is I to the power of 1 divided by I. Because this part here is just the root. And I said before, 1 divided by I doesn't look too cool, but we can, again, extend it and multiply the numerator and the denominator by I. This will give us I to the I to the power of minus I, because this here becomes -1. We've just done this before, and then the minus moves to the numerator in front of the I. And I to the power of -I is just 1 divided by I to the power of I. And this one here, we've just calculated before because we said I to the I is e to the power of -pi divided by 2. So we can just say, well, this is 1 divided by e to the power of -pi divided by 2. And this will be e to the power of pi divided by 2. And this gives us something like 4.81048 and so forth. I know this is probably quite tough for the first round, but it's all in the slides. There are proper solutions. It's probably typeset of what I've just shown you. And this is all the knowledge you need about complex numbers for this course. That also means you'll have some time until next week for revision up to here. That's what I've just shown you. In the course, you will probably not need such stuff anymore, like the ith power, the ith root of I and this kind of stuff. But I just wanted to put this in to challenge you a little bit. Next week, we will look at vector spaces. So you remember vectors and matrices, how to add them and all of this. We will briefly revise this next week. Look at briefly again what vectors and matrices are and what their fundamental operations are. And once we have done this, we will plug complex numbers into our vector spaces. And there are a few new concepts that we'll explore next week of what you can do in a matrix or a vector with complex numbers. And these are super important operations that we will need in our quantum gates in a couple of weeks. So we're just building the foundations for all we need in our fundamental quantum gates. So the complex vector spaces next week, we will finish. This will maybe take half an hour to 1 hour. And then next week, we will directly dive into systems and we work towards describing quantum systems, then look a little bit more into quantum theory. And then we have all the foundations we need to build our quantum gate. So it's still a few weeks of lots of maths working towards quantum theory. But then once we have all of this, we can build our quantum gates, look at algorithms, theoretical limitations, applications, and eventually your seminar presentation. It's all doable. And the course is not examined by a written exam, but by a seminar presentation for which there's lots of flexibility on your side. But we want that you understand quantum computing in detail in this course, and that it's not just high level. Now, are there any questions from you now towards the end? If there is a question, maybe just raise your hand here in the chat and I'll see if there's something to wait for. With there not being any questions, we're done for today. The recording will appear later in YouTube and I'll link it in the iLearn course. And as I told you, next week, the lecture is already on Thursday because I'm busy on Friday with the hiring committee. And I've also posted all of this in iLearn already. Enjoy your weekend, also revising this course. See you next week and take care and bye-bye.